Okay, we're all here, right? Yes. So, yeah, it's my pleasure to introduce our speaker for this week's seminar as Paolo. Andrea Erdman. Paolo and I, we did the PhD together in Scuola Normale. We worked almost every year together during our PhD, and it's a real pleasure to have you here, Paolo. And he's going to talk about reinforcement learning and how reinforcement learning can be applied to quantum thermal machines and devices. Paolo, I stop to you now.
Yeah, thank you, Bidek, for the introduction. Yeah, so let me see if I can share the screen. Okay, can you see my screen properly?
Yes.
Okay, yeah, so as Bidek said, we did our PhD together at the Scuola Normale, working almost daily together, and now I'm doing my postdoc at the Freie Universität in the group of Frankenoy. And yeah, in this presentation, I'll be talking about how we use reinforcement learning to find optimal cycles for quantum heat engines. And some of the results I'll be presenting were done together with people from the University of Geneva, in particular Alberto Rolandi, Paolo Bius, and Martí Ferrarnau-Lobet. So yeah, so first I'll give a general introduction to what are quantum heat engines and how do we describe them. Then I'll show how we use reinforcement learning to optimize the power. And then I'll briefly mention how we extended this method to make it applicable in principle to experimental devices to have a model-free method. And then how we generalize this method to optimize the trade-off between power efficiency and power fluctuations. So starting from the very beginning, so from an abstract point of view, we can describe a driven heat engine in terms of these following three objects. So we have a hot bath, we have a cold bath, and we have some system, which in a classical case could be a gas and a piston, but in a quantum case, this would be our quantum system that could be, let's say, a qubit or a particle or an Ising chain, for example. And the idea of a driven heat engine is that in time, we can decide to couple the system to the hot bath, and this would enable some heat exchange, heat flux JH. We can couple the system to the cold bath, and this would enable a heat flux JC. And most importantly, we have a set of time-dependent controls, UDT, that allow us to influence the state of the system and to exchange work with it. So for example, if this control in this case was the position of the piston, by changing the position of the piston, so by expanding it, we can, for example, extract work from the system or put work into it if we compress the piston. And the two main thermal machines I'll be talking about is the heat engine, where we want to extract work exploiting a temperature difference, and the refrigerator, which is a system where by putting work into the system, we want to cool a cold bath. And so what do I mean by quantum or nanoscale heat engine? So let's say classical system is something which typically is a macroscopic system. So we have in mind something, for example, with an Avogadro number of particles. And because of this, the state of the system is typically close to equilibrium. So we can describe, for example, the state of a gas instead of solving the trajectory of all the particles. We can describe it in terms of pressure, temperature, volume, and so on. And typically, we have small fluctuations in the thermodynamic quantities because of the large number of particles or degrees of freedom. In the other extreme, we have nanoscale systems or mesoscale devices, which can be, for example, where this working fluid could be, as I was mentioning, let's say a single particle, an ion, or an electron, or even a qubit, which arguably is the smallest, let's say, quantum system. And here, typically, so we have very few degrees of freedom. And because of this, the state of this nanoscale system could be far from equilibrium. So we really have to solve for the quantum state of the system. And we may also have large fluctuations in the thermodynamic quantities. And this is something that will be relevant in the last part of the presentation. And by fluctuations in this context, I mean the following. So let's assume we have some system, which could be a gas in the piston, initialized in some state. And now we act on the control parameters to do some transformations. So for example, we expand and we recompress the piston, and we look at how much work was put into the system. And let's say this was W0. Now we repeat the same exact transformation starting from the same state, and this time the work is perhaps W1, and so on. And the reason why this could be different when you have few degrees of freedom is intuitively clear if you take the limiting case, let's say, of a single particle. So if in this gas you just had one particle, let's say if you hit the particle while compressing the piston, then you're exchanging work with it. But if the particle was trapped in some corner, then and you don't touch it during the expansion, then the work is 0. So this means that by repeating many times the same transformation, we can have different outcomes for work and heat. And in this sense, work and heat are stochastic quantities. So one can talk about work distributions and work fluctuations would then be quantified, for example, by looking at the variance or the width of the work distribution. So just to briefly mention some solid state platforms where people have started to do experiments in quantum thermodynamics. One of them is superconducting circuit QD. So this is a device that was fabricated in the group of Jukka-Pekkola at the Aalto University in Finland. And here in the center, you see, for example, a superconducting qubit, which is coupled to these two resistors. And these resistors act as heat paths. So as a heat path, a source of microwave photons for the qubit. So here what they were able to do is to apply a temperature difference, and the qubit is coupled through these coplanar waveguides to the resistors. And after applying a temperature difference, they could really measure the heat flowing through the system in steady state conditions. And now they're planning to control the qubit in time through this other line and to try to implement, let's say, thermodynamic cycles on a qubit. Another platform would be perhaps quantum dots. So for example, here, this is a device that was fabricated in Pisa, and this is an indium arsenide nanowire. And in the center of this wire, they fabricated a quantum dots, a region where you can confine electrons. And then they applied a temperature difference across the device. So they have a temperature gradient across the quantum dot, and they were able to drive a charge current induced by the temperature difference against a voltage bias. And this is a way to extract work in steady state devices. And another platform are trapped ions. So one can consider as your working fluid, or as your system, let's say a single ion, which is trapped within these optical traps. So, but from a theoretical point of view, which is what I mainly work on, how do we just characterize the performance of a heat engine? So when I talk about a thermodynamic cycle, what I mean mathematically is some periodic modulation of our controls UDT. So by describing what is the shape of the control that we repeat in time, this is a way to describe a thermodynamic cycle. And this includes cases, for example, one can describe as special cases, Carnot cycles or Otto cycles, but in general, one can consider any modulation of your system in time. And the performance of a heat engine is mainly characterized by its power, which is the ratio of the work extracted after one cycle divided by the duration of the cycle, tau. The efficiency, which is the work extracted by the system divided by the heat provided from the hot bath. And then for technical reasons, it'll be more convenient for us to consider the average entropy production instead of the efficiency. And then power fluctuations, which, as I mentioned before, we can describe in terms of the variance of the work distribution divided by the duration of the cycle. And the main question we want to try to answer is, what are the thermodynamic cycles? So what are these functions UDT that can maximize these quantities? So if we just optimize the efficiency, if we're just interested in the efficiency, we know since Carnot that we have to do reversible transformations. But typically these are infinitely slow, which means that ideally you could reach Carnot efficiency if you didn't have friction and so on. But this typically, and you could also have zero fluctuations, but this would happen at zero power because it would take you an infinite amount of time to perform a single cycle. So the ratio of work divided by time goes to 0. Then one can try to optimize the power. And this is something which is much more model specific. So there's no universal recipe of how to have a cycle that maximizes the power. So this is also a more complicated task to achieve. But let's say numerically, we can optimize the power. And even if we can reach the maximum power, this typically happens at an efficiency which is lower than Carnot's efficiency. And the fluctuations of the power are typically large in these nanoscale systems. And again, if one is just interested in power fluctuations, again, one can do reversible transformation, which means that we can have low fluctuations, high efficiency, but low power. So this is all to say that there's a fundamental trade-off between these three quantities that ideally we would like to optimize simultaneously. And one interesting consequence of this trade-off are the so-called thermodynamic uncertainty relations that were introduced in this paper and other papers by same authors and then studied a lot in recent years. So the original formulation is the following. So they showed that for classical systems in the steady state, so for heat engine, the steady state, which means these are systems where you apply a temperature difference, you apply a voltage difference, and then you wait for the steady state to occur, and you look at how much at the properties of the system. So then in this work, we focus on driven system, but what they showed is that for steady state engines, the following inequality holds. So if we define psi, this quantity, which is a combination of power, fluctuations, and efficiency, this combination is bound to be smaller or equal to 1. And this has various implications. So for example, if you try to attain Carnot efficiency, so if you set eta equal to eta c, in order to satisfy this inequality, you either have to have 0 power or vanishingly small power or diverging fluctuation. So this is an interesting consequence of this trade-off between the three quantities, but this doesn't give us a full picture of the trade-off between these quantities because, well, first of all, these, as I mentioned, these hold for steady state engines and what we are studying are driven heat engines, which it is known that they can violate this formulation, the TUR, but it's still being investigated. And most of all, let's say from this inequality, one would imagine that a good engine has a large ratio psi. So one would think that when you saturate this equality or to maximize psi, this might be a good engine. But this might happen in the limit, for example, of low power or of low efficiency. So in general, this doesn't give us a full description of this trade-off. So what we do, we use the concept of Pareto optimality, we search for these so-called Pareto optimal cycles. And these are by definition the cycles where you cannot further improve one quantity, say the power, without sacrificing the other ones. So we have this general definition of Pareto optimality, which helps us when you have multiple objectives that cannot be optimized simultaneously. And we define optimal cycles in this context as those where you cannot further enhance one of your objectives, so you cannot further improve one of the quantities without sacrificing another one. And the collection of all of these Pareto optimal cycles defines the so-called Pareto front. So if you imagine to have a space where on the axis you have power, efficiency, and fluctuations, the Pareto front would be all those cycles where you cannot further improve a quantity without sacrificing another one. And we'll see some examples further on if this is a little too abstract at this point. And mathematically, one way to find this Pareto front is to define this figure of merit F and to try to maximize this figure of merit F. So what is this? This is a convex combination, so a linear combination of our three objectives. And these A, B, C are just some positive coefficients, so some numbers that sum to 1. And the idea is if the Pareto front is convex, then we could optimize this F for many different values of A, B, and C. And the collection of all the cycles that we find optimizing F for many values of A, B, and C will give us this Pareto front. And intuitively, for example, if we said A equal to 1 and B and C equal to 0, what we're doing, we're just maximizing the power. And these negative signs here are because what we want to do is to minimize the fluctuations and to minimize the entropy production. And as we move the weight from A to B and C, what we're seeing is that we're caring more about minimizing the entropy production or about minimizing the power fluctuations. So yeah, the general idea would be to repeat this optimization for many values of A, B, and C. And now let's see, how do we compute these quantities for quantum heat engines? So in a quantum thermal machine, what we have in mind is that our system in the center now is some quantum system, let's say, for example, a qubit. And for the moment, we are describing the system in the most heat engine, the most simple way. So we consider that our quantum system is weakly coupled to the heat bath. And under the Markovian approximation, you could show that the reduced density matrix rho, so rho is the reduced density matrix of our quantum system, satisfies the Lindblad equation, which is this first order differential equation for the state rho that has these two terms. So we have one term that describes a unitary evolution of our system in the presence of our control. So those control parameters that I mentioned, UDT earlier, enter through the local Hamiltonian H of our quantum system. And then we have the dissipative terms, one for alpha equal to H, so the hot bath, and C would be the cold bath. So we have these terms that describe what is the impact of the thermal bath on the evolution of our state rho. Ideally, now we could solve for rho given some cycle U. And once we know rho, we can compute the instantaneous thermodynamic quantities in the following way. The instantaneous power is given by the trace of rho times H dot. And this is a pretty standard expression in quantum thermodynamics. And the entropy production is just given by the sum of the heat flux divided by kT. And here we do not include the entropy variation of our quantum system because once we apply cycles and we reach the limiting cycle, then also the state will be periodic. So essentially the contribution to the entropy of your system will be 0, and you only have entropy production given by the bath. And then we can compute the heat fluxes, J alpha, as a trace of H times the dissipator corresponding to the bath alpha. So these are relatively standard expressions in quantum thermodynamics. But what we want to do is also to compute, and then we need to average these quantities over a cycle. So then the average power and the average entropy production would just be the average of these instantaneous quantities averaged over the cycle. But in order to compute also the power fluctuations, these cannot be computed just from observing rho. So taking the expression of the power fluctuations from this paper, we showed that we can introduce this quantity S. So this S would be an operator with the same dimension as rho. So if this was a qubit, rho would be a 2x2 matrix, and also this S would just be a 2x2 matrix, but that has a 0 trace. And it satisfies this different first order differential equation. And if we introduce this quantity, then we show that we can compute the fluctuations, the power fluctuations as a time average of this delta P of t, which is given by the trace of S times H dot. So this is a mathematical trick that then will be useful later on to use reinforcement learning to also optimize power fluctuations. So the general goal is, the idea is that if we have a cycle UDT, we can solve the Lindblad equation and we can compute these quantities rho and S. Given rho and S, we can compute our thermodynamic quantities, plug them into the figure of merit. And our goal is to find what are these cycles that optimize F. So there have been various approaches in literature to try to optimize, for example, the power, the efficiency of these cycles. So for example, one can fix the structure of a cycle. So one can fix, for example, an octocycle and just optimize over a few parameters that characterize the cycle. We'll see some examples also later on. One can consider the slow or fast driving regime, where slow and fast means compared to the typical thermalization timescale of the system. So if the driving is slow compared to the time that it takes the qubit to thermalize, or fast, then there are some papers that try to optimize the power in these limiting cases. Another approach is to take cycles that work well in the adiabatic case and the infinitely slow case and try to speed them up, for example, using shortcuts to adiabaticity, which is a technique that can emulate the adiabatic behavior of closed quantum systems in finite time. Or else people have tried also variational approaches, for example, the Pontryagin maximum principle. But all of these approaches do not, except for the number 4, do not guarantee that we actually find optimal cycles in the sense that we truly optimize the power, the efficiency, or some combination. So what we wanted to do is to use reinforcement learning to have a method that doesn't make any assumption on the structure of the cycle, nor on the speed of the driving, or hardly any assumption on the driving of the speed of the driving. We want to be able to handle noise ideally in the controls, and we want it to be applicable eventually also to experimental devices. And yeah, I'll further discuss this later on, what I mean with this last point. So now I'll move to this to the first result. So for now, we'll just focus on the maximization of the power. So this would be the limiting case where we set B and C equal to 0, and we just care about optimizing the power. So I'll say a few general words about what is reinforcement learning. So reinforcement learning is a general optimization method that allows us to solve optimization problems that are formulated in the following way. So some computer agent has to learn how to master some task by interacting with some environment. So let's say we take time and we discretize it in time steps. At every time step, the computer agent can choose what is an action AI to perform in the environment among a set of possible actions. And this action is typically chosen according to a policy function pi, which is a function that describes what is the probability of choosing action AI given that the environment is in some state Si. So the environment is in some state Si, and based on the state of the environment, the computer can choose some action according to this policy function. And then the environment returns what is the new state at the next time step. And this the new state will depend on what was the action chosen and what was the previous state. And it also provides a reward. And this reward is just a scalar, it's just a number. And the aim of reinforcement learning is to learn what is an optimal policy pi that optimizes the sum of the future rewards that you would obtain in the future. So what you want to learn is what are the optimal actions at every step that don't just optimize the single reward, but we want to optimize the sum of the rewards that we will obtain in the future. And this is a gamma to the power I, where gamma is called in literature, in the reinforcement learning literature, a discount factor. So this gamma is just a number between 0 and 1, which is fixed. And this sets essentially what is the time scale over which we are optimizing the sum. So for example, if gamma is close to 1, we see that here we are really summing over many terms. But if gamma is close to 0, then this decays exponentially, and we're just summing over the next few rewards. So this gamma pretty much sets what is the time scale over which we're actually optimizing the sum of the rewards. The way we applied this to the optimization of the power of a heat engine is the following. So we chose as action that, so again, we discretize time in small time steps dt. And at every time step, the computer agent can choose an action which is made up of two quantities. The first is this UI. So these are the continuous controls that we have within the Hamiltonian. And it can choose any continuous value within some intervals. So it can choose some continuous control UI. And it also chooses a discrete action DI, which corresponds to choosing whether the quantum system is coupled to the hot bath, to the cold bath, or none, means essentially that it's doing a unitary evolution. And the reason we allow the agent to choose at every time step these three actions is because in typical thermodynamic cycles, you do have a stroke when you're coupled to the hot bath, then you have a stroke when you're coupled to the cold bath, and then you decouple it and you do some adiabatic transformation. So in principle, we want to give the computer agent the flexibility to construct any kind of cycle. And then as a state for the reinforcement learning algorithm, we simply choose the reduced density matrix rho of our quantum system. And as reward, we choose what is the power that was delivered during the last time step dt. So the reward is just the power delivered by the engine during the last dt. But since the aim of reinforcement learning is to optimize the sum of the rewards, in the end, we will be optimizing the power averaged over a longer time scale. And this longer time scale, capital T, depends, of course, on your time step dt and on this gamma, which was that discount factor that I showed in the previous slide. So essentially, if we choose gamma to be close enough to 1, we will be maximizing the power averaged over a very long time scale. And because of this, the computer agent should learn that it should just repeat some cycle over and over, and it should automatically also determine what is the optimal period of the cycle that maximizes the power on the long run. So from a more practical point of view, to see how this works, let's say this is your control U as a function of time, and at some time t0, the heat engine is in some state rho 0. So based on the state rho 0, the computer agent will choose some action. And this action would be, for example, to set the control U to some value U0. And this orange color means that it chose the discrete action of coupling to the hot bath. Now, and we keep the control constant for a time dt. And at the end of this, we compute what is the state by solving the Lindblad equation. We compute the state rho 1 at this time t1. We compute the reward R1, which is the power delivered during this time step. And based on this information, the computer agent will make another action. So we will have, for example, different value of U, and again, coupled to the hot bath, and so on and so forth. So by iterating between these two objects, we will end up constructing a piecewise constant cycle or control, and so on. Okay, so we first, and the method we use is the so-called soft actor critic method for those familiar with reinforcement learning, where essentially you learn two quantities. One is the policy, which is what I described earlier, and the value function is defined in the following way. So the value function is the sum of the rewards that you would obtain if you start from state S, you perform action A, and then you choose all future actions according to the policy pi. So in the soft actor critic, let's say language, the value function essentially is the critic. So it's a function that tells you how good a certain policy pi is. And the policy would be the actor, because the policy is a function that chooses what actions to perform onto the environment. And mathematically, there's a theorem that tells you how, if you know what is the value Q of a given policy pi, it tells you how to find a better policy pi prime. And once we have a policy, we can evaluate it and estimate its value Q. So by iterating over this policy improvement step and this policy evaluation step, we can converge ideally to an optimal policy. And okay, so first we tested this method in the most simple case and in the only case where we knew what is the analytic optimal cycle. So here we just consider it as a working system, a two-level system, so a qubit. And so we just have sigma z. So essentially the Hamiltonian commutes at all time, and we have no coherence generated in the instantaneous eigenstates during the evolution. And our control is the gap of the qubit. So here we see what is the power, the average power of the engine as a function of the training steps. And each step is one of these small dt steps that I mentioned earlier. And these here are what are the actions? So what are the controls u as a function of the step that were chosen in these three different points at these three different moments during the training. So we see that at the beginning, we just initialize the system with a random policy. So the controls here are completely random, as you can see here. And also the color, which is the discrete action, hot bath, cold bath, or unitary, is completely random. And the corresponding power, in fact, is negative, because as you can imagine, if you just do random things on an engine, instead of extracting work, you will be dissipating work in the form of heat into the environment. But then as the training goes on, so with this reinforcement learning method, we see that the power slowly increases, some structure appears in the chosen actions by the policy, and eventually we reach some plateau to some value of the power. And the final control that achieves this power is given by the square wave. And this is in fact what we proved analytically to be the optimal cycle just in this very specific simple case. So the optimal cycle is just coupling the system to the hot bath for the shortest possible time. So here it would be just for a single time step dt. Then you abruptly couple the system to the cold bath, and you also change the control u, so the gap of the qubit to a different value. And you keep jumping between these two different values of the control and the two different baths. And this dashed line is the upper bound that we derived analytically in this paper. So we know that at least in this simple case, the numerical method can find the optimal known solution. So next, we applied it to a system of which we do not know what is the optimal cycle. And this was essentially pretty much a description of this device that was fabricated by the group of Jukka Pekkola. So they also proposed this model. And here, what we have is this superconducting qubit, and we want to operate it as a refrigerator. So the Hamiltonian here is again a qubit, but we have one term proportional to sigma x that we cannot control. This depends on some circuit parameter. And then we can only control the prefactor, the sigma z term. So here, when we change the control u, we're also rotating the Hamiltonian, meaning that we're generating coherence in the instantaneous eigenbasis of the system. So yeah, the Hamiltonian doesn't commute at different times. And since they couldn't explicitly choose which bath is coupled to the system, they coupled the qubit resonantly to these two, the two heat baths, meaning that we will choose parameters such that if u is equal to 0, we'll be in resonance with the cold bath. And if u is equal to 1/2, we'll be in resonance with the hot bath. So essentially, if you want the tunneling rates to the hot bath and the cold, to the hot and cold baths are really peaked around certain values of u. And this allows us, by controlling u, both to change the state of the qubit, but also to choose which bath is coupled to the system. So what we find is the following. So here, this is now the cooling power, again, as a function of the step. And again, at first we have these random actions. And in the end, we converge to the cycle given by this black thick line. So as we expected, we jump between 0 and 0.5, which as you can see here, you see the coupling strengths to the cold bath and to the hot bath as a function of u. So as expected, we are alternating between the hot bath and the cold bath. But in between, there's also this additional control on u, which perhaps not very intuitive, which is some control that is done essentially when you're decoupled from the bath. So this, if you want, is some unitary transformation that it's doing between being coupled between the hot and the cold bath. And what we did, we compared to the cycle that was proposed in this paper and in the previous ones. So in those papers, they tried to maximize the cooling power by trying a sine wave or cosine, trapezoidal wave and square wave. And what they found is that the trapezoidal wave provided the highest power. And they also optimized it over the period. So they found what is the period of this trapezoidal wave that optimizes the power. And the intuition is that if this trapezoidal wave is too slow, of course, the power will be low because it takes a long time to perform a cycle. But what they showed is that even if you go too fast, then the refrigerator will stop working. And this is because when you start going fast, you will start to have non-adiabatic effects. So you will generate coherence in the instantaneous eigenbasis. And in this context, this is known as quantum friction. So it was shown that this generation of coherence, at least for this specific application, has a detrimental effect on the power. And this detrimental effect becomes so strong that if the cycle is too fast, then the refrigerator stops working. So in the end, there's this intermediate optimal period that maximizes the power. And the corresponding power to this trapezoidal cycle is given here by this dashed line. So what we see is that the cycle that we found actually has a cooling power, which is roughly 5 times larger than the one found optimizing over this trapezoidal cycle. And I think this could be intuitively explained in the following way. So if we look at the period of the cycle that we found is roughly 5 times shorter than the period of the trapezoidal cycle, which means that we're extracting the same work per cycle, but just 5 times faster. So this might mean that we are somehow mitigating this quantum friction, or this detrimental effect of quantum friction. So what we did, we actually computed the average coherence that is generated by the 2 cycles by operating them at the same speed. And we saw that, in fact, our cycle generates half as much coherence as quantified by the relative entropy of coherence, which is some measure of the coherence. So it does, produce half as much coherence. And I believe that this allows us to operate the cycle faster without having this detrimental effect. And then the last case we analyzed was a quantum harmonic oscillator. So this would be where our working fluid is an ion, for example, trapped in a parabolic potential. And what we're controlling is how open or closed is this parabolic potential. And notice in this case, the Hamiltonian doesn't commute at different times. And here we operate again as a heat engine, and we find again that we find some value of the power. And this is given by the cycle here shown as a thick line. And what we did, we compared it to this paper where they studied the same exact system, but they optimized the power with respect to Otto cycles, where an Otto cycle would be this dashed line here, which is made up of these 4 different strokes. And here they optimize the power over the duration of these 4 strokes. So if one does this, we find this dashed line. So we see that our cycle, which is actually surprisingly quite similar to the Otto cycle, actually has a slight improvement in the power. It's not very relevant, but it still has a slight improvement. And this perhaps is due to the fact that you can actually modulate the control while you're still coupled to the hot bath or to the cold bath. And then we just repeated the same optimization, but we allowed the agent to choose the actions in a larger interval. So here we constrain the actions to the small interval to enable a fair comparison to this paper. And here we allow it to choose bigger values of U. And we see that we can do slightly better also in the power. Okay, so now just in this last part, I'll briefly show how we extended this method in 2 different ways. So one problem of the current method is that we use as state for the environment the density matrix. But the density matrix is quite model specific, but mostly it cannot be measured experimentally on a device without perturbing the system. So one cannot imagine to measure the density matrix at every dt while performing these cycles. So what we assume in this paper, we assume that the agent only has access to the heat currents J alpha. Essentially, it can only monitor what are the heat fluxes that are leaving the heat bath. And the only physical assumption that we make is that the heat current at time t depends on the control that you applied, so on U of tau and D of tau, only for value of tau between the time t and t minus t history, where this t history is some time scale that sets pretty much the memory of the system. And actually, in open quantum systems, this t history is some finite quantity. So for example, in a Markovian system, this would be just a thermalization time scale. Because in fact, if you imagine, put a system in contact with a hot bath, once you thermalize, you will reach a Gibbs state regardless of what you did in the past. So in open quantum systems, the dissipative effect actually creates this finite time scale t history. And in this method, we also assume that the computer agent has no knowledge of the Hamiltonian, of the dissipator, so it's completely a black box approach. So it can only see the heat current and it knows nothing else about the system. So what we do, we use as a state for the reinforcement learning method, the sequence of actions that were chosen between t and t minus t history. So this is some implicit way to, if you want, to encode the state, because in principle, if one knows what are the actions that were applied between t and t minus t history, you could reconstruct the state. And if you reconstruct the state, you can reconstruct the heat fluxes. But yeah, so we only expose to the reinforcement learning algorithm what are these actions that were chosen in this time frame. And then the aim in this case, what we try to optimize is this combination between the power and the entropy production. So the C is some number between 0 and 1. So for example, if C is equal to 1, we are just optimizing the power. and if C is equal to 0, we're minimizing since there's a minus the entropy production. And for intermediate values of C, we will find the so-called Pareto front. So we applied it to the same system that I described earlier. And here what we do, so we perform the optimization of this figure of merit F for many values of C. And these are the values of F that we find. And for each of these, we report here on the right, what is the corresponding value of the cooling power and of the COP, so the coefficient of performance, which essentially is the efficiency of a refrigerator on this plane. So by repeating this optimization for many values of C, we find all these points which describe the Pareto front. So for example, if we're interested in a high power refrigerator, then we should choose cycles in this area where we have the highest power, but a relatively low efficiency. Or if we care more about efficiency, we should choose cycles in this region where we have higher efficiency, but at the cost of lower power. And these are, for example, how some of these cycles look. So these are cycles that are given by these blue dots here. So this is, for example, when you only care about power, we find these quite fast cycles that have this different shape now because we chose slightly different system parameters as compared to before. And as C decreases, so as we shift our what we are interested in from power to efficiency, we see that the cycles become slowly larger, slower and slower. So the period becomes longer, and this is kind of intuitive. If you want more efficiency, then also the period becomes longer of the cycle. And and this is using this black box approach, so where the reinforcement learning agent doesn't know anything about this Hamiltonian. And then we applied it in the same exact way also to the harmonic oscillator. And again, here we find this Pareto front, so this trade-off between power and efficiency. And and we see that as compared, for example, this would be the Pareto front that you find if you optimize only over Otto cycles, which are these trapezoidal ones. And we see that we have a higher power than the Pareto front of the Otto cycle. And we could also match the efficiency if we choose points in this extreme. And for example, this is the cycle that maximizes the power, and this is the cycle where we care more about efficiency. And we can see that again, the period becomes longer, and we have again these unitary strokes, if you want, between the hot bath and the cold bath. And now in this last part, I just want to quickly mention this work where we want to really optimize this trade-off between power, fluctuations, and entropy production. And if before we were using a state, the density matrix in the original work, what we did now is that we had to extend the state to include this other quantity S, which is the one I mentioned earlier that allows us to compute also the fluctuations. And we choose as reward simply the average of the time average of this figure of merit averaged over time step dt. And here we considered again the simplest possible system. So we just have a two-level system with no coherence. If you want, this is just a stochastic classical two-level system. But here we treated both the gap of the two-level system and the inverse temperature beta as continuous controls. And the intuition was that maybe if you care about efficiency, it's also convenient to slowly vary the temperature between two extremes. This will turn out to be not true. We always do jump between the hot bath and the cold bath, but in principle, this is how we set up the problem. And what we know already from before is that if we only care about the power, so in the limiting case of A equal to 1, then these fast Otto cycles are optimal. And these fast Otto cycles mean the square wave, which has very high frequency, where you just jump between two values. So what we did, we also studied the system analytically in these two limiting cases. So in the fast driving means that essentially we try to optimize F even when when we care about multiple quantities among all possible square waves. So we just optimize over the position of these two lines, and we optimize F. And the slow driving regime, also we performed an optimization of F, and this was the main work that was done by the University of Geneva, by Martí, Paolo, and Alberto. And okay, so here we see, so here we performed one optimization. So what we want to do is to optimize F from many values of these weights A, B, and C. So here we have the weights, the value of the weight A and C, and here we just choose B such that the sum is equal to 1. And we repeated each of these dots corresponds to a separate optimization of the figure of merit with these different values of A, B, and C. And what we did, we put a red dot whenever the figure of merit is optimized by one of these fast Otto cycles, and a blue dot whenever reinforcement learning can do better than these fast Otto cycles. And what is interesting is that we see that the fast optocycles are not only optimal when you care about power, but they're optimal whenever we are on the side of this triangle, which corresponds to when we're only interested in two objectives. So when we only care about power and efficiency or power and fluctuations, then these optocycles in the fast driving regime are optimal. But as soon as we care about all three quantities, we see that we can do better with the reinforcement learning method. And here, this is just a contour plot of the figure of mirrored F computed with the reinforcement learning method. And this is how, for example, some of the cycles that we find in these points. So for example, if we take a point on this diagonal, for example, this point, here we see what are the controls. So beta is inverse temperature, and it's given by the black dots. The blue is the control U, and here we have time in expressed in units of the 1 over the thermalization time scale. And if we zoom in here, we see that it's actually jumping between the hot baths and the cold baths and between two values of U as fast as possible. And these are indeed those fast optocycles that I mentioned earlier. But for example, if we take this point here where we care about all three quantities, we find, for example, this type of cycle where we jump between the hot and the cold baths, but we have also some modulation of the control U in this linear fashion. And as we move down in this plot to this lower point, and this lower point means that we care less about power and much more about efficiency and fluctuations, we see that we find these extremely slow cycles. Because here, if you look at the scale, the period here is like 200 times the inverse thermalization time scale. So these are very slow cycles that are very well described by the slow driving regime. So we see that as we move around this the space on the side of the triangle, we're in the fast driving regime, and the lower part, the optimal cycles are in the slow driving regime. So we can compute this Pareto front, which now is a 2D plane in this 3D space of power, fluctuations, and efficiency. And we computed it restricting to the fast driving regime, slow driving regime, or using the numerical method. And what we see, for example, here in the fast driving regime, what is interesting is that the outer border here of the Pareto front corresponds to when you only care about power and fluctuations. But we know that whenever we care about two quantities, these fast optocycles are truly optimal. This means that this outer border that we found analytically is actually the exact border of the Pareto front. But then we know that here, these are the values of the efficiency that we find in between, and these may be suboptimal if we only use these fast optocycles. And what was interesting is that we showed that in the fast driving regime, this TUR ratio, so this quantity psi, is exactly equal to 1. So by moving around this equation, we see that the relation between the power and fluctuations is in fact linear, and the angular coefficient is given by the efficiency. So this is why with these contour lines are these straight lines. This just comes from the TUR, setting this TUR relation equal to 1. But now if we look at the slow driving regime, as expected, we cannot reach the border of the Pareto front, because the border is when we only care about two quantities. And when we care about two quantities, we're in the fast driving regime. So that's why we cannot reach this border. But what we see is that in this regime of low fluctuations, we can have higher efficiency. So here the color is around purple and blue instead of being, let's say, green and red, which means that we have a higher efficiency as compared to these fast optocycles. And with the reinforcement learning, we pretty much have the best of the two limiting cases, because we see that we have points, so we have cycles along the whole border, and these red dots correspond to these fast optocycles. So when we only care about two quantities, we lie on the border, but we have a very low efficiency. However, if we sacrifice very little power, we see that we could have these points that are green or blue or bluish, which means that we could be really close to the border, but still have a much higher efficiency as compared to these fast optocycles. And yeah, so we see that there's somehow an abrupt change in the optimal cycles as soon as you go from 2 to 3 quantities that you're interested in. And then to conclude, we plotted what is the value of this ratio xi that is known that it can be greater than 1 in driven systems. And here we have a contour plot of this xi, again, as a function of a and b. And we know that on the sides of the triangle, we're in the fast driving regime, so it's equal to 1. But here in the center, we see that we can violate, so we can have values like xi bigger and bigger and close to 100 here in this lower part of this plot. And in fact, if we plot xi as a function of the power, entropy production, and fluctuations, we see that xi is diverging in the limit of low power, low low entropy production, and low power fluctuation. And it's diverging as a power law because this is a log-log plot. And since we know that in this regime, the slow driving is a very good approximation, we actually derived what is this power law using the slow driving regime, or the people in Geneva did. And we see that there's a nice match between the numerics and this analytical black curve that was derived in the slow driving regime. So yeah, so to conclude, I just summarize quickly. I first gave a quick introduction to quantum heat engines. Then I explained how we use reinforcement learning to optimize the performance of quantum heat engines. Briefly discussed this model-free extension of the method to be applicable in principle to experimental devices where we can monitor the heat currents. And then we perform this full optimization of power, efficiency, and fluctuation. And I think as future directions, it would be interesting perhaps to study more complicated systems, so to really study some many-body system as working fluid, or to go beyond the weak coupling regime. So for example, in this model-free approach, we could in principle apply the same machinery also to a system which is not described by Lindblad dynamics. And another interesting direction that we're now exploring also together with Vivek and Andrew Jordan is to include explicitly also quantum measurements and feedback, and see if by learning what are, for example, optimal measurements or optimal feedback, if we can further enhance the performance of these engines. And reinforcement learning is a flexible enough framework that would allow to do this in a pretty straightforward way. And yeah, this is it, and thank you for listening.
Hi, Paolo. Really nice talk and work. I was wondering, could you please explain again the distinction between the continuous and discrete action? When
Yes.
the discrete action comes into play in optimization.
Right. So let's see, for example, in this case, so what we want to do is to optimize, for example, the power of this engine, where you have this control, which is here the frequency, let's say, of the harmonic oscillator, or maybe it's more clear in this case, it would be the gap of the qubit. And we assume that the computer agent can choose a value of the gap of the qubit within some continuous interval. So for example, we say choose values of u between, I don't know, 0.1 and 1 in these units. And this means that it's a continuous action in the sense that it can learn in principle any value of u that is continuous within some interval. Here would be, for example, 0.1 and 1. And the discrete action would be instead whether you want to couple your system to the hot bath, or couple it to the cold bath, or to just do unitary dynamics. And mathematically, and this is discrete because we only have 3 choices. It's not a continuous action within some interval. And mathematically, this would be switching off in the Lindblad equation. If it's unitary, you would just be evolving your state according to this first term. If you're coupled to the hot bath, you would include this dH, so the dissipator corresponding to the hot bath. And if you choose the discrete action cold bath, you would just include dC, so the dissipator related to the cold bath. So yeah, and this was to mimic, if you want, standard cycles like Carnot cycles or Otto cycles, which usually they're formulated in terms of isothermal transformations when you're coupled to like a hot bath, or then you have an adiabatic stroke when you're decoupled from the bath. So we wanted to give it the possibility to learn in principle also standard, let's say, cycles.
Thank you.
I think Domenico has a question.
Yes, my question was about what happened when you have situations where your reward is kind of not changing much across different possible strategies. Mm-hmm. So we know that reinforcement learning is prone to this kind of issues when there are very complex systems. So in these simple systems, have you seen explicitly situations like this? And do you think you're going to encounter them for multi-body problems, since this is one of the directions that you plan to explore?
Yeah. So as you say, this is not a gradient-based method. So you're not really taking the gradient across the differential equation and really going in the direction of gradient. So And it's also a stochastic approach. So what happens is that at the beginning, you have this trade-off between exploration and exploitation, which means that at the beginning, you have to explore many different actions, and then at some point, try to find a more and more deterministic policy. And because of this, you have a lot of stochasticity. Also, during the training, then this policy function and the value functions are parameterized with these neural networks, and also the training of these neural networks is stochastic. So you're right, there is some degree of variability. And for example, when what I showed in this plot here, let's see, in the second case, just repeating the same optimization. So here we repeated the optimization of, let's say, the figure of merit at some given value of C, and we repeated it something like 6 or 7 times. And we see that this is like an error bar. So every time we find a slightly different solution. And if you look at also the Pareto front here, it's not a perfect line. So there is some noise, let's say. So,
but qualitatively quite similar in this case. I mean, there is an error, but doesn't.
Yeah, exactly. It's quite small. Yeah. So I mean, we do see, of course, it's a stochastic method, so there is some, let's say, error bar, but it's relatively small. I mean, at least on this scale, it doesn't have a big impact. And this method here also does not look at the density matrix, so this is even more prone to these kind of errors. So when you really use the density matrix during training, it's quite stable, I would say. So in some other cases now I'm optimizing, so not for heat engines, but a different application. I'm looking at systems whose state is parameterized maybe by a few hundred parameters. So your rho would be parameterized in terms of, let's say, 100 real numbers, 150 or so. And there it still works reasonably well. It could get stuck in suboptimal cycles, that is true. I mean, you have to play around with these hyperparameters a bit to really get it to converge. So yeah, so if you don't time things properly and you don't allow it to explore enough, it might converge to some suboptimal cycle, or it might even learn that it should do nothing. Because what is funny is that at the beginning, during the training, the power is negative, right? So for example, here you see that the power is negative, and doing nothing, which means just setting a constant U or decoupling the system from the bus, would give you 0 power. So doing nothing would certainly be better than doing random actions. So sometimes I was getting stuck in doing nothing. This was happened at the beginning, for example. But yeah, if you're careful enough, I think it can be pushed to pretty big systems. So yeah.
Okay, thank you.
I have a question. In this slide that you have here, you see this sort of strange pattern that you get into you wouldn't have guessed a priori. And you gave us some kind of hand-waving explanations about what this little stutter in the middle is doing there in terms of like doing some kind of unitary action or something like that.
Yeah.
Once the computer shows you these patterns, do you ever like stop and say, I don't know what the heck is going on here? Is there a way of trying to get better insight into why this kind of solution is the best?
Yeah, I guess a better way would be, I mean, one way to gain more insight. So one thing we did was to compute this coherence that is generated in the instantaneous eigenbasis. And we saw that in fact, this extra feature here allows it to generate half as much coherence. And we know that coherence is detrimental for this application, or it decreases the power. So this was, I mean, one semi-quantitative explanation. But yeah, perhaps it would be interesting maybe to really plot what is the density matrix or some parameterization of the density matrix by using these 2 different cycles to see, for example, on the one, so since this is just a qubit, we can see on the block sphere what this is doing, if it really is trying to align the state to the Hamiltonian such that this coherence in the instantaneous eigenbasis is smaller, and that I didn't check. So that would be probably worth checking, yeah, to really understand better what is happening. So I think maybe plotting what is the state that you would get with these given cycles would give you more insight, because otherwise, right, you get these weird features and it's not clear why this is happening. So given a system, you can find the best solution, but then you need to, yeah, study it kind of carefully to learn something more general or more, yeah.
Thanks.
Abhishek.
Yeah, I had a question about the model-free approach that you're doing. So when you go from taking the density matrix as the state to this sequence of actions, I don't know which slide that was on, but
okay, I guess it was here. Yeah.
Yeah, right. So in this new method, where you're using the sequence of actions to be the new state of the system. I think this sort of leads off one of the previous questions where one of the other problems you run into such sequences is a delayed reward problem. Is that some, or more generally, the sort of temporal structure of these actions? So which action corresponds to what effect? Because there might be long time correlations, at least experimentally, if there's a lot of actions before you get a feedback. So is there anything you're doing for that?
Okay, so yeah, so the idea, in fact, of incorporating many time steps in the state is in some sense to give it access to this longer term correlation. So to really see what was applied before, because yeah, the state at time t does not only depend on what you did at the last time, but there's some correlation with your control in the past. So yeah, and because this reinforcement learning method is based on this Markov decision process, which means essentially that this reward and the evolution, so the evolution of the state and the reward must only be a function of your state and of the last action that you apply. So this way of augmenting this the state is some way to make it apparently Markovian, even if it isn't. So you embed more memory of the past within the state, within what you call state. So I'm not maybe really sure what you mean by delayed reward. So I mean, for sure, this is a harder problem because now the state space is huge. So here you have, for example, we took, let's say n could be 128 or 64. So the input now to your network is a sequence of 64 or 128 numbers. So, okay, so here we use some specific architecture based on these convolutional neural networks to try to decrease, so to process these time series in a kind of efficient way. But yeah, in principle, it is a harder problem to learn for sure, because before you just had 3 numbers, the numbers that of the density matrix essentially. So some, let's say the block vector, and now you have the sequence of numbers, and an action might have a few components. And yeah, so the learning in principle is much harder. Then in these simple cases, it seems to converge pretty much to the same solution and a reasonable and the same number of steps. But of course, each step takes longer for the computer to do all the gradients, descent, and so on, because this is they're more complicated networks. So yeah, so then it is slower in training in the end, yeah.
Can I ask a follow-up to that, since you mentioned convolutional nets? So since this is temporally structured data, typically recurrent neural nets are used for temporal structures. Well, so is there a particular reason you chose convolutional nets?
Yeah, so it was this. So my supervisor, he's really into machine learning techniques, but not as much into these quantum physics problems. So yeah, so one idea was exactly to use recurrent neural network, which is a way to embed, memory from the past. But he mentioned that there was this paper by Google that's called WaveNet, where they essentially process time series in this kind of fashion. So you have many inputs, and then you pretty much, process them 2 by 2. So in some sense, these are like 1D convolutions with a kernel of 2 instead of 2. So the vague idea was to try to copy this architecture, to copy this idea that it's used to process, let's say, sound, and to mimic and to process this series pretty much in a similar way. So maybe I have somewhere a slide with a picture of the what the neural network looks like. It's not super clear, but not the best, but okay. Yeah, so we have these oops. Yeah, so we take, let's say, if you have an input with, this would be n, this would be your time series. So we apply this 1D convolutions to these 2, then to these 2, 2 and 2, and this produces 4. And then, so essentially you are halving the length of your time series at every step. So we define this, let's say, as a convolution block that goes from length n to n half. And we do this by applying some convolution network that only acts on these 2 and produces this. And then these 2 produces the second one, and so on. And then we stack multiple of these. We stack multiple of these convolution blocks such that we have the size of the input, and we just end up with a single, let's say, input with many channels, and then we apply just some fully connected layers. And so I mean, the intuition was this WaveNet paper by Google, where they were not using this other method for time series, but they were using pretty much this kind of convolution idea. But yeah, I haven't tested. I think the other approach would have worked as well, I guess, but I haven't tested it.
Okay, thank you.
So if there are no further questions, let's thank Paolo again, I guess.
Yeah, thank you all for the possibility to present my work at IQS, and yeah, maybe talk to
Nice
you.
talk.
Thanks. Hey, see you.
Bye.
Bye.